Good afternoon. First, I would like to thank organizers to give me this opportunity to give my work, even though I'm not expert on the string theory. Yes, I mainly work on some inflation models, but when I kind of apply this talk, I thought I can have enough time to explain what is the inflation or no boundary measures, but I found 15 minutes is not enough, so I will just focus on this one of my topics, which is no boundary measure, and then this work is ongoing. It's almost done with these are my collaborators in Korea and in German, and I hope you can find this paper this week or next week on archive. So let me start with yes, and first probably I have to apologize first because I'm not an expert on the quantum gravity as well. So this talk will be very kind of introductive level. So you can find very probably too good and too simple or too easy. But I will try to explain what is no boundary measure, and then why we consider this measure using this multi-field inflation models. And then I will show the probability, how the probability will change with from this multi-fields. And then I will conclude. And if time allows, I will show the future work. So what is no boundary? So we so far as I know, we cannot explain or cannot solve the kind of the nature of the initial singularity of our universe. So one conservative approach to solve this problem can be to canonically quantize the universe and study the wave function of the universe as a solution of relativity equation. So this wave function depends on the boundary conditions, and then although there is no trivial way to determine which the boundary conditions, so one kind of appealing choice will be the ground state can be as a wave function of our universe. So Hartree-Hawking suggested the Euclidean path integral as the boundary condition of our universe, and then show that that's also a solution of these equations. And this one is just kind of repeat this explanation as just a graphical way. So let's say this area is our present universe, and we want to know the probability of here, and then there's singularity, and we try to kind of explain this our universe as using the wave function. By the way, this slide is from one of my collaborators' talk. And because this wave function depends on the wave boundary conditions, so there will be there is possible to have some other boundary conditions like this. So wave function will have kind of large value on our universe, but there will be kind of small but non-zero other possible histories like this, infinite number of other possible histories like that. So we can say this is there is no more boundary conditions anymore. So this one is no boundary. Yes. So we can just see our universe, history of our universe, and then we start with time as introduced by the complex time, so like this. So we start complex time and then turn into the usual Lorentzian time till now. So there can be various analytical continuations, and if this path is regular, we will choose this one as our history of the universe. So again, if if we say this cone is our history of the universe, we cut this singularity part and then try to find the geometry over the complex time until the geometry to be regular, and then we believe the action there. So with this no boundary measure, we can have some probability function in terms of number of foldings and E here. With the slower inflation model with the quadratic potential, we can have the probability function which looks like this. So this one shows this no boundary measure kind of prefer the our universe has smaller number of foldings, so which is not really compatible because we widely accept our universe needs to more than 60 foldings from inflation. So how can we understand this one, or how can we solve this problem? So simply we can say the inflation is not enough, so we can just abandon and then introduce some other alternative models. Or even though this probability is low, we can also have this our universe in terms of in context of eternal inflation and multiverse. Or directly we can just lift up the inflationary probabilities. For example, Hawking and Hartog, they introduced this additional term inside of probability, which is they called volume factor. And as you can see, the probability becomes like that. So this probability can lift at a large number of fields and large number of foldings like that. But we think this is not really kind of natural or reasonable, because it can be some other shape, or we don't quite see why they introduced this specific type, shape. So we try to kind of motivate it ourselves, or to see if there is kind of an effect if we introduce a large number of fields from inflation. So for example, inflation models we will use in this context. So we will see how the probability will change from these multi-field factors. So what is inflation? Inflation, I will just briefly say, originally proposed by Dimopoulos-et, and then this inflation model is one of multi-field inflation, and then in this model, the large number of fields needed to have enough foldings, like several hundred fields for like 60 foldings. So all fields have some Planckian value for initial conditions. So, and we chose this initial condition as randomly chosen within this cutoff. And for simplicity, we make these models quite, the simplest way. So the quadratic potential type, M squared, phi squared type, and then this mass as same mass. So this makes phi easy in this model. So I will just directly go to the probability. So this one we now obtain from our models, and then this one is from usual factor from Euclidean probability, as I showed you before, and then this one is from the multi-field factor here. This one NF is the number of fields, and this mu tilde is the mean value of number of foldings. So when the number of field has mean value, this effect has a kind of maximum. So, and as you see, this probability also kind of you can see the 1 over m squared is yes, this one. So when number of fields increase, so this probability becomes getting smaller, and then some point it's getting smaller than this peak. So this one becomes kind of dominant effect under this probability. So yeah, and we need this this point. So this number of fields can be larger than the 1 over m squared. So we need kind of a scale of this mass, so we can see how many fields are needed to have this effect. So from inflation model with the same mass, the calculation is quite easy. And then from power spectrum, from the W map, we know the power spectrum, and then from there we can renormalize the scale of mass. So we have the mass, it's 10 to the minus 6 scale, mass Planck mass. So we have the number of fields is larger. If the number of fields is larger than 10 to the 12th, we can see we have kind of effect from the multi-field factor here. So we kind of see this result is quite too large number of fields. So because maybe we can say because this is just a first try of this no-boundary measure to the multi-field, we can kind of hopefully reduce this number of fields by introducing other generalized model parameter in future. So other parameters are just the same as like this. So I'm not sure how many times I have, but I will conclude. So I will just summarize, and I showed what no boundary is, and then I showed the inflation model with a Planckian cutoff. And then with this setup, we need a large number of fields, and this large number of fields can enhance the inflationary history without adding some other factors when the number of fields are larger than the order of 10 to the 12th. And then based on this very simple model, we can kind of have apply some generalized, some more generalized model, like when the fields are different, or when the mass is not constant, or not quadratic potential type, but cosine type of potential can be considered. Or we can apply to some other inflation models, like non-slow inflations, or introduced by some new light fields, like curvature scenarios, etc. Okay, thank you for attention.
You said you need a huge number of fields to achieve the inflation. What is the mass scale for these particles? I mean, is it a kind of, can it be String scale, or should be much smaller?
Mass is, I've shown, is 10 to the minus 6.
10 to the minus 6
Planck mass scale.
Planck mass.
Yeah. And
that is below the String scale, so that probably not possible in the context of string theories. And second chapter and so on cannot be counted.
Maybe we are around that scale, I guess. Yeah.
It's the actual scale.
Yeah.
It's not around that. But it's strange, it's really good.
Yeah, too many, I think.
So, I mean, I think there might be a kind of a entry problem with this many fields, because I mean, there's a kind of contribution to entropy which, well, basically goes as number of fields times the cutoff scale squared. And it seemed that your scaling was such that, like, the number of fields times their mass scale squared was always going to add up to the Planck scale squared. At which
around it, yes.
Yeah, at which point you start worrying, because this is also basically the rate of the de Sitter entropy, and you've got trouble. You've got kind of too much stuff. And
yes.
you can give an entropy kind of measure which says you've got more AC entropy that you're possibly allowed by
yes.
string theory. I mean, this is related to the worry that you can't. The string theory might not give you any models with that number of fields.
Yes, I think that's an interesting point to think about the entropy things, but yeah, I just realized that your the paper is, but I not quite fully understand how to. But yes, probably I should read more carefully and then discuss this.
Great. So if there are any more questions, why don't we ask during the break, which we have now. Well, let's thank everybody.